Hello, everyone, and welcome to the Canadian Electricity Association's Conversation webinar series. CEA is the voice of the electricity industry in Canada. My name is Farhan Mirza, and I'm pleased to be your host for today's webinar. I'd like to begin by acknowledging that the land on which I'm broadcasting you from today is the traditional unceded territory of the Algonquin and Anishinaabe people. The Algonquin peoples have lived on this land since time immemorial, and I'm grateful to have the opportunity to be present in this territory. I'd also like to recognize Canada as the land of the First Peoples, Inuit, and Métis. I would like to pay homage to the Indigenous peoples past, present, and future that continue to work, educate, and contribute to the strength of our country. I would like to recognize that the land is shared through historic treaties, developed through contemporary treaties, and one that continues to be unceded territory. The Conversation series features presentations from CEA's corporate partners, and the series will highlight a variety of Canadian and international solutions to current and future challenges faced by the industry. Working with CEA's corporate partners, these webinars have been developed to be of specific interest to those working in the electric utility space from generation through to the customer. For a list of upcoming sessions, you can check out our website again at electricity.ca. Before we get going, there are a few housekeeping items I'd like to go over. Our session today is scheduled to go from 1 to 2 p.m. Eastern Standard Time. Questions can be asked, and we'd encourage you to do so by, as they come to mind, by typing them into your chat function on the screen. Questions function. They'll be asked at the end of the presentation. And lastly, a brief survey will be sent to webinar participants following the session today. We very much appreciate your candid feedback and are interested in any topics you'd like to have covered in the conversation series in the future. And please keep an eye out for our future webinars and events through CEA's monthly newsletter, Current Affairs. With over 6,000 subscribers, Current Affairs, much like the national newspaper, is the place to go for Canadian industry news as we connect the national value chain from generation through to the customer. If you'd like to receive current affairs, you can subscribe to this free publication on CEA's website, again, at electricity.ca. Moving on to today's session, on the conversation series today, I'd like to welcome Asasoft Canada, who will be presenting on characterization of silicone insulator surfaces to understand chemical, electric, and algae resistance. Polymer insulators are gaining attention as attractive alternatives to traditional ceramic or glass designs on account of their prolonged resistance to water ingress, lightweight, and greener production footprint. However, comparably less is known about how polymer materials such as silicones react and adapt to environmental conditions, including chemical stress from de-icing salts, electrical stress from service delivery, and biological stress such as algae adhesion. Today's presentation will introduce some of Asasoft's latest silicone-based insulator products and present some research and highlights from our ongoing materials characterization efforts. To take us through today's presentation, I'd like to welcome Rajkumar Padmawar, President and CEO of Asasoft Canada, and Dennis Four, Professor at the Department of Chemistry at the University of Victoria. Gentlemen, welcome to the conversation series, and Raj, I'll turn it over to you.
Thank you very much, Farhan. It is a wonderful opportunity here to present this subject matter. And thank you very much to CEA for having us make this presentation today. My name is Rajkumar Padmawar. I'm from Victoria, British Columbia. As you see, British Columbia is into state emergency at this point, and it's there until January 18th. And the crew has been working very hard, and thanking them immensely, and also the CEA to be able to bring this on air. So no further ado, so this is about the characterization of the polymer insulators, and as you know, the skin of the polymer itself and the skin of the metal that is exposed to the environment is what actually keeps that insulator functioning and stopping those electrons moving. So the picture here you would see in the left is the picture that is taken in San Francisco, where you would see some of the ASA insulators that is helping mitigate or improve the safety in the fire season. And on the right, you would see a picture where our affiliate partner, Kodak, is parting with a knowledge that they have acquired in the last 100 years for a better yesterday, better today, and better tomorrow to our younger folks. Go to the next slide, please. So here is our quick story. We've been actually collecting a lot of feedback from the utilities in Canada and the United States and across the planet. And we have about roughly 5 million of these field tested in about 19 countries, ranging from minus 80 to plus 54. So on the right-hand side, you would see there's a picture from Death Valley, California. And the one on the left, you would see that's Antarctica, where the temperatures could actually go into as much as minus 80 as the lowest recorded temperatures. And there's a quick take on Kodak, which is our affiliate partner, and has been parting a lot of their experience for us to actually move these insulators to the next level. And there's a little history of British Columbia with Kodak, where Northern Electric was very instrumental in getting the power lines active in British Columbia. Go to the next slides, please. So here is quick challenges that are associated with most traditional components, and possibly that can be mitigated using the polymer insulators. The list could be as big and as small as it can be, because every insulator has its own use in the field. But more importantly, we would like to bring in some of the areas that would actually really be interesting for the larger community. And that is mainly how we could actually bring in the algorithms, and how we can actually bring in artificial intelligence, the machine learning, and also more importantly, the predictability of insulators, basically from lab to the lineman, and close the loop with lineman to the lab. And here we present our the research and development into the micro level of moving our research level into developing those data and mining that data. I hand in this to Mr. Dr. Hoare, University of Victoria.
Thank you very much, Raj, and thank you everyone for joining us here today. So it's my great pleasure to tell you about some of the work we've been doing to look at these materials on a microscopic level in collaboration with Asasoft to get a better understanding of this insulator performance. And the story really starts with the idea of hydrophobicity. So this is a concept that I think many people are familiar with, since it's an everyday phenomena that people can observe. But briefly, the term hydrophobic itself, the origin of the word, it stands for water fearing, so materials which fear water. And it's the opposite of hydrophilic, or materials which are water loving and like to be interacting with water. And the classic example of hydrophobic materials are things like leaves, or things like a Teflon pan, where if you put a drop of water on the surface, it'll beat up in terms of trying to avoid the contact with the surface as much as possible. And in the opposite case, the classic example of hydrophilic is a very clean piece of glass. If you have a horizontal piece of glass and it's super clean, and you put a drop of water on it, it'll spread to cover the whole glass. And one of the reasons people are so interested in hydrophobicity when it comes to silicone insulators for power line applications is that it's understood that this is one of the reasons why the materials have such a good and prolonged performance. And it's been noted in the field that once the hydrophobicity starts to decline, this eventually leads to water ingress and the premature end of life of these insulator materials. So how can this be evaluated? Well, from a very crude perspective, you could simply put a drop of water on the material and make an assessment with your eye to see whether it's starting to spread on the surface or if it's still beating up. And in fact, the STIR method is nothing more than a visual inspection of the contact angle. In the lab, you can look at this more analytically by taking a picture through a microscope and then just going into Photoshop and actually drawing a tangent line and characterizing this contact angle. And there you can come up with a definition like less than 90 degrees is hydrophilic, more than 90 degrees is hydrophobic. So you can say that there's a 135-degree contact angle for silicone rubber, for example, when it's clean. And when the surface is aged or contaminated with algae, the contact angle drops. Now, the problem with this definition is that it's too macroscopic. And in the slides that I'm about to show you, I hope to convince you that this is not really a sufficient definition because it doesn't give us enough information. On the one hand, if you can look at a material which has failed after some time in the field, and you can see that the hydrophobic nature has decreased because the contact angle has dropped, you can see there's obviously a change in the contact angle. But this really is not a very good predictor because we don't really see a change in the contact angle of materials up until that point. So it'd be nice to have a more detailed microscopic description of how the material ages before we get to the point where we have to see a loss in hydrophobicity and water is no longer beating up on the surface. So just to give you a little bit of an overarching picture here, in my lab, we're really interested in studying the interaction between liquids and solid surfaces. And this is why it's just such a great collaboration with Asasoft. And I was really fascinated to learn about this project. And there are three tenets to this approach. Here I'm showing you that in gray, imagine that this is the silicon rubber. And now you could have a certain, cross-link structure of this rubber and a certain chemical nature of the structure and the bulk. But on the surface, the very, very surface of the material can be quite different from the bulk in terms of composition, in terms of how the molecular functional groups are oriented. And all of this is really important for environmental considerations because the very tippy surface really interacts how this material interacts with this environment. And one can even say that all of the bulk silicon rubber is responsible for the mechanical properties of the rigidity and the flexibility of the material, but the surface is responsible for everything that we're really interested in the current topic. But one of the things my group's interested in is the three-pronged approach here, and that is that if you really want to understand how things interact with materials, looking at the surface of the material is only one part of the picture. And the second part is looking at how the water looks like right at the surface of the material. And here we can see, for example, if we change the water conditions, if we add salts, so we're interested in de-icing salts, for example, we can change the silicon rubber and we can change the water. So you can picture this as the environmental conditions like the water, the salt water, you have materials in solution are changing the rubber, and at the same time the rubber is changing the environmental conditions of the liquid. And this is really what happens on a molecular scale. So you would ask why, or maybe I should say you should ask, why would someone care about this at such a detailed microscopic level? Well, the reason for that is simply now, if we look at pollutants or even larger species like algae on the surface, and we want to understand why is the algae sticking to the surface under some conditions? Why is algae not sticking to the silicon surface under other conditions? How can we make sense of that? My view is the way we make sense of that is by closing the loop and looking at all these things together. So let me give you some few specific examples of what we've been working on. The first project I'd like to tell you about here is one where we designed some custom flow cells with different dimensions that we can flow liquid through. And the idea is that the bottom of the flow cell, the floor of the flow cell, is made of a silicon rubber. In this case, we're using polydimethylsiloxane, PDMS, which is one of the most characteristic members of the silicone family. And what we do is we fill these flow cells with algae, and then we have a very simple setup where we have a pump, which is just a computer-controlled syringe, and the computer can basically push the piston of the syringe and flow solution over the algae, which are adhered onto the silicon on the base of the flow cell, and then back out through another piece of tube into a waste beaker. And the way we do this experiment is we put algae into the chamber, we let them adhere onto the surface, and then we gradually increase the flow rate of the solution. And as we do that, what happens is eventually the algae will not be able to hold on anymore. And as the flow rate increases further and further, algae become detached from the surface. So this is all computer controlled, and we synchronize taking videos together with knowledge of how we've stepped up the flow rate. And the basic idea of this experiment is, since we know the volume of the syringe and we know the rate at which the motor is pushing the piston through, we know the flow rate, the volumetric flow rate. But since we know the dimensions of the flow chamber, we know the wall distance, and we know the distance between the floor and the ceiling where the algae are adhered, we can calculate the shear rate. And then finally, from some fluid mechanics calculations, if we know what the shape of the algae are, we can actually quantitatively look at the force in newtons that the algae are experiencing as they get faster and faster velocities of fluid rushing past them. So what the raw data looks like is we see what fraction of the cells are adhered as a function of the force they experience. So this 1.0 on the left-hand scale of my graph, maybe 200 algae cells are adhered, and eventually that number becomes 150, and then it's 100, and then it's 75, and in the end you have only 10 there, and the rest are all washed away. And this is really exciting because we can characterize the adhesion strength as a function of a whole bunch of different environmental conditions. So the first thing I'll show you is once we had this set up, we were very curious to see what difference would it make if we had the algae adhering onto the surface for 15 minutes before we subjected them to this washout stress versus if we gave them nearly a day or 20 hours to adhere on the surface. And the the hypothesis is that if they get a chance to interact with the surface longer under quiet conditions, they may be adhering more strongly. And we observed just the opposite. And this is very interesting for the field studies because you can see that even a very brief exposure to algae causes them to stick just as strongly as if they had a chance to actually secrete more substances and be stronger adhere, which is not the case. And the other interesting thing here is if you look at the values of the force along the horizontal axis of my plot, and you compare this with the typical force that's exerted by environmental conditions like wind and rain, it shows you that even minutes of algae adhesion results in cells which are stuck onto the silicon surface more strongly that can be removed just by things like wind and rain force. And this really goes to show why it's such a strong problem of fouling of insulators by algae. But the real big study that we wanted to do, and the reason we set this up in the first place, is to do a comparison between different environmental treatments of the base of the flow cell, which is where the silicon rubber is. And what we have done is we've compared pristine silicon rubber with a silicon rubber that's been soaked in water for a month, for 30 days, before assembling it onto the bottom of the flow cell, versus a piece of silicon rubber which has been soaked in a saltwater solution for 30 days before making it via the bottom of the flow cell chamber. And when we did this, we compared two different species of algae. One is T. rotula, which is an ocean algae, which is not very sticky, but we picked this because it's a very cosmopolitan species. The species is found in all coastal areas across the world that have ocean exposure. And then the other species we compared to is a very sticky fouling species, which is a freshwater species. So this would be found basically on insulators on power lines, which are next to lakes or rivers or freshwater areas. And in both cases, what we found is that the adhesion strength of the algae decreased with increasing silicon environmental exposure. In other words, the algae were more likely to come off to the surface or not as strongly adhered onto the silicon if there was treatment with either water or salt water. And the salt treatment had even a greater effect in the sense that the algae wasn't adhered so strongly. So this is very fascinating, and we wanted to understand why this is the case. So now it comes back to the materials problem. How has this environmental exposure actually affected the silicon rubber? What's happening there to make it more or less susceptible to the cell adhesion? Well, to return back to what I was telling you about contact angle, the first thing we did is we measured the contact angle quantitatively through a microscope, characterizing the shape of this droplet. And here we saw that in all cases, pristine silicon rubber, water soaked and salt soaked, we really see no difference at all in the contact angle. So this goes to show you that this is too macroscopic of a probe. So whatever happens to the silicon rubber, which makes the algae adhere more or less strongly, we really can't capture any of that with contact angle. So the other thing which is often discussed is that the roughness of the surface changes on a micro scale. But here you can see that even with a nanometer probe of the surface roughness, there's really no change in the surface becoming more or less corrugated as a result of environmental exposure. So this can't account for it either. So then what we did is we decided to go to an optical probe, which could give us a micron level description, looking at the top 1 micron, which is 1,000th of a millimeter of the surface. And to do this, what we do is we bounce infrared light through a prism, and then it interacts with the silicones. We put the silicone upside down so it contacts the prism, and we collect a spectra. And these two peaks that you can see here on the left-hand side basically show you the symmetric and anti-symmetric stretching of the methyl group. This is a carbon-hydrogen functional group on the surface of the silicone, which is responsible for imparting hydrophobicity to the material. And you can see right away from the data, the take-home picture is even by looking at the top micron of the material, we basically don't see any change in the structure. So if that's true, what are we left with? What's happening to the surface during environmental exposure, which makes it so important for the algae? So now we realize that we need a probe which can be looked at a very finer level, because even though a micron sounds like a very small distance, 1,000th of a millimeter, truth is that a micron is a huge distance when you consider the length scale of the individual molecules, individual polymer chains that make up the silicone. So here in gray at the bottom of my stack, I'm showing you the bulk silicone rubber phase. In black, I'm showing you the top nanometer, and I say nanometer because that's roughly the length scale of the molecular chains. And then I show you all the different length scales of the solution phase. So these could be in red, it could be the proteins secreted by the cells, which mediate their interaction with the surface. In the darker blue, I'm showing you that special water that I talked about on one of my first slides that's being affected by the silicone structure. And now we get into the bulk water phase. And the thing is, this whole interaction distance has a length scale less than 10 nanometers. So we need a way of probing very, very fine structure like this. And it's difficult to do this with any kind of probe, let alone optical probes. But in our lab, we have one trick up our sleeves. And this is one of our specialties in the characterization, is we use a type of nonlinear optical spectroscopy. And basically what we do is we use two lasers, and I'll show you a photo of the setup in a second. One of the lasers is in the visible at 532 nanometers, and one of the lasers is in the infrared. And when you come in with two pulsed high power lasers and you overlap those beams on the surface of the silicon rubber in space and in time, something very special can happen. What can happen is, in addition to the normal phenomena that you would observe, those two photons can be annihilated. And if those photons are annihilated, there's two laws of nature which must be observed. One is conservation of energy. A new photon has to be born, and its energy has to be the sum of the energies of the two photons that died. So in other words, we make a new color, and that's why this is called three-wave mixing. And if we know the color or the frequency of the visible light and the color of the infrared light, we know where to look for this new light. And the second thing that happens is momentum has to be conserved. So if you know the angle that those two lasers came in at, you can basically understand where to look for this very rare photon creation event. So the question is, why do we do this? And the reason we do this is because this gives us a depth resolution of approximately 1 nanometer. And what's so special about this is that only the molecules at the very top of the silicone rubber are able to create this new light in blue that I'm showing you. So it actually doesn't matter how far our beams penetrate into the bulk silicone phase. We can excite, microns or millimeters of the material, but the only signal that we get is from the molecules at the very top on a nanometer length scale. So this is what the experiment looks like. It's a bit of a Frankenstein setup here. So I'm showing you in the back, there's a laser, and then I just annotated this here on the slide just to show you with a green line. This is where the visible light comes and approaches the sample. And then we make a high power infrared pulse, and this is where the infrared light comes and approaches the sample. The green light's reflected off the sample, we don't care about it. The infrared light's reflected off the sample, we don't care about it, because that's not the very extreme length scale we want. To get that extreme length scale probe, we want that new light that's created, which I'm showing you in blue. And just to give you an idea of how rare this event is, it's so rare that you need such a high powered visible light. We have basically 10 to the 16 photons in every pulse coming in the visible. We have 10 to the power of 13 photons of infrared, and we make 10 to 20 photons of this upconverted light. So we're basically doing single photon counting. But this is what gives us very special information. So before I show you the data, I'm going to show you one more photo, and that is a photo looking straight down onto the sample so you can understand where the silicon rubber sits in this experiment. And if I were to take a drop-down view of the very middle of where the sample is in this area right here, you can see it looks like this. So here's your incoming green laser, here's your incoming infrared laser, and in blue, these are just the few photons which are created just from that top nanometer of the surface. And what you see here is a hemi-cylindrical prism, and this is just a glass prism. But right where I'm showing you the dashed black line is where we coat the silicon rubber. So if we just coat silicon rubber on the prism and we don't do anything else, then we can look at the silicon air interface to within a nanometer length scale. But underneath this kind of stirring motor I'm showing you is a liquid chamber, and I'm showing you a cutaway of the chamber diagram down below. And we can fill that chamber with water, with salt water solution, and now we can look at the surface of the polymer and the liquid. So we can look at any kind of environmental condition and see what's happening at the top nanometer. So when we do that experiment, this is basically the result that we get. We see something which is a vibrational spectrum because we're using infrared light. So just like I showed you before, we have this methyl group symmetric stretch, we have this methyl group anti-symmetric stretch. But what's really special is that all of the data points that you can see that make up these spectra came from just a nanometer at the top of the surface. And the first thing we can see is, unlike that 1 micron length scale probe, which was 1,000 times deeper than what I'm showing you here, now we see a substantial difference between the different environmental conditions, particularly with respect to salt. So one of the main areas of interest in my lab is to take these spectra and to do some modeling to understand what does this mean in terms of the structure of the material. How can we understand this? And what we do now is we basically figure out how has that molecule oriented to give us this kind of picture. And basically what we can see is what I'm showing you here is a silicon atom down below, and then we have one moiety, which is methyl, and another moiety which is methyl, because every repeat unit in the silicon chain has these two methyl groups. And we can imagine a plane between these kind of three moieties. And what this analysis has shown, if I go back one slide here, is that these spectra indicate that the plane of the methyl group is tilting with respect to water exposure and saltwater exposure. So this is a very small change. It's not as if this methyl group is suddenly burying itself into the bulk silicone phase and is flipping upside down. It's just subtly changing in tilt and twist angle. So who cares about this? The algae care about this. So it's amazing that this small change doesn't show up in terms of surface roughness. This small change does not show up in terms of contact angle, and yet this small change is something which really triggers the cells to have a difference in the behavior on the surface. So if you want to find out more about this, I've got a link on the bottom, but you can also look at this on my website, and on the Asasoft website we have a link if you want to see more full details of this study. So just before I pass it over to Raj to tell you a little bit more about Asasoft and the products, I'd like to tell you about some future ongoing work that we're doing. And so far, I've told you about the chemical stress and the salt exposure. I've told you about the biological stress with the algae exposure, but there's one missing part, and that is the electrical stress. And after all, these are insulators, which are subject to high voltage. That's the purpose of the material. So how could we study this together? So we kind of have two approaches here. One is bringing the samples into the lab, and the other one is bringing the lab to the samples. And the first approach we're pursuing is to take our setup that offers this nanometer length scale probe where we can really see what those chains are doing at the silicon surface and put electrodes there so that we can put some high voltage across. And the preliminary results are really interesting, and what they show is that we can see that the surface hydrophobic groups, these methyls, which are important for imparting hydrophobicity to the silicone rubbers, are changing with response to the applied field, and they are also affected by the polarity of the field. So you can imagine that if you have an AC field here, these methyls are flipping back and forth on the surface very rapidly. So one of the ways we used to think about loss of hydrophobicity of these materials is that the methyls are changing their orientation over time and are not being able to stick up as much as they used to be when the material is pristine. And the more we study this phenomena, we have a very different kind of molecular picture as to what's going on. It's a much more of a dynamic picture where these chemical functional groups are flipping back and forth very rapidly. And then over time, as the material ages, just like our bodies, like our elbows and our knees when we get older, we're not able to go through that full range of motion anymore, and it kind of slows down because there's so much motion that happens in these pristine materials on the microscopic scale. So we're really interested in these experiments, and they're really poised to provide information on the mobility of these surface functional groups. Another thing that's really interesting, if you look at the chemical structure of the silicone rubbers, the silicon oxygen bond is really what is the most polar part of the molecule. So this is what really is expected to move with respect to the electric field. And yet what we're probing is the silicon methyl group, because that's the part that is imparting hydrophobicity to the material. So it's almost like the silicon oxygen bonds move with response to the field, and the methyl groups are along for the ride. And so this is very interesting to understand the relationship between these. So then finally, this is the microscopic picture, but we also are engaged in the macroscopic version of this experiment. And this is a very fancy tracking wheel that we're just putting the finishing touches on. And so many of you may be familiar with tracking wheels already. The way this works, basically, it's a device which can provide chemical and electrical stress for insulators. Ours has a few very special characteristics that we're really proud of. First of all, you can see that there's two tanks here in the photo. So one of the tanks can be filled with, let's say, sodium chloride solution, and the other tank can be filled with magnesium chloride. We can look at different de-icing salts. And then you can see two wheels or two rotors, and on each side we can mount up to 4 insulators. And one of the things that's special about our design is that we can accommodate insulators of different lengths and different profiles, dead end, station posts, different types of configurations, all on the single side on the single wheel. So we can mix and match lengths and sizes on one side. And then what happens is this thing rotates, the insulators take their turns being dunked into the tank, then they come out of the tank at the 3 o'clock position, they move into the 12 o'clock position, they're subject to high voltage, they cool down in the 9 o'clock position, and they get dunked again. And furthermore, our design has an automated lift mechanism built in, so we can program wet and dry cycles as they come in and out of the salt solution to look at sunny days and salt exposure days all at the same time. And this is all computer controlled with a HMI interface and a PLC where we can log and we can monitor all the characteristics. So we're really excited about the ability in our lab to look at these types of realistic exposures and combine this with our nanometer leg scale probes of the surface to see what happens on these actual materials from these insulators. So now I'm going to turn it over to Raj, who's going to tell you some additional information about Asasoft.
Thank you very much, Dr. Hoare. That was a fantastic deep dive. And a quick take on having to move on to the lab to the lineman. And again, from having to discuss a little bit quick on the subject of having to treat as defend the corrosion and the moisture ingress. So one of the technologies that we use is Coric as a Armagolf, and which is field tested for about 3,000 hours of salt fog with no corrosion, and it can go up to 10,000 hours. But more importantly, we wanted to present to you those 2.0 insulators that has a mediated French surface of polymer and the metal as well. So these are the few of the awards that we won for the product. And here's a quick deep dive into the Armagolf, which is basically a thermal diffusion process by Distech Corporation. And Coric out of San Francisco, California, has pioneered the electrical hardware with Armagolf, and what we actually got in is basically to further engineer that to the insulator usage. As you can see here, the byproduct of having to use the technology, you would actually get to use only 1% of you get to basically reduce about 99% of the solid waste and the water waste. And when the process is complete, you would actually see a complete mesh of a corrosion-resistant material, which is zinc, which is integrated into the metal as one surface, which can even be used to the next processes like grinding. And you would get a complete stainless steel grade corrosion resistance with 1/5 of the cost of stainless steel. And you would see a classic Navy chain there. If you're actually in any of the Bay Areas, you would see ocean areas, you would see those Navy chains. Or this is an example from the Navy chain from Coric, and you would see the one on the left is basically with a hot dip galvanizing. The one on the right is with the Armagolf. And this has also won an award from EPA as the most valuable pollution prevention method for corrosion resistance. And why today we are doing this is basically, as you see, most of the infrastructure in the United States and Canada combined needs a replacement, and about 41% is near to end, and 4% is already end of life. So if we were to actually put the demographics together, it's $1 trillion that's going to be invested in the next 20 years, as per Harris and Williams. And just a deep dive. So what we are doing here is we brought in the entire insulator that is basically for the distribution, bring in those characteristics of transmission grade insulator into a distribution. And the reason that is being done is because the component of that 1 trillion that is going to be invested in the next 20 years is mostly for the distribution part of the segment of moving the power. And if you actually look in the distribution, we're looking at basically from the substations to the homes, as you would see these on your boulevards. So there's a quick conversation here as a recap. As you would see, even though the insulators only contribute to 5% of the infrastructure cost, but having to go back and replace them, it costs more than 50%. So this is very important to have a good insulator, and this probably the timing is right to actually do a next level of research into this and have to bring in the right insulator for the right environment, and also to differentiate between an insulator which is suitable for which environment. So without further ado, so what we did is we actually brought in all the industry problems into this one chart, and also hazards and issues, and a few of the areas where Asasoft is contributing is on the third column here, with lightweight, the next level of longer lifespan, next level of self-cleaning, irrespective of how they're exposed to a different de-icing salts that is used in US and Canada. More importantly, the polymer construction itself, and having to bring in the component, which is thermal diffusion Armagol for Obviously Corporation with Cordic, and having to bring that product in a way that is mostly plug and play into the field. Thank you very much, Dennis.
Thank you. So I'd just like to conclude by thanking some of the people on the team who've done some of the work that we were talking about today. Shaful Azam has performed all of the nonlinear optics experiments with the lasers to look at that top nanometer of the surface. Kanu Kai has been doing the modeling to come up with the orientations of those surface functional groups from those experiments that Dr. Azam was working on. Celebi Wan was the one who's done all the algae adhesion experiments to look at the shear rate of those cells as they get flushed off the surface. This is with the help of Ben McVicker, which wrote the software that coordinates the image acquisition with the pumps and the cameras and all of those things. Harrison Fletcher came up with the initial design for a lot of the computer control of the tracking wheel. And Kevin Darshan is currently working on finalizing and optimizing some elements of that tracking wheel for the next stage of our experiments. I'd like to take this opportunity to thank CEA, our sponsors of this event, once again for the opportunity to present this information to you, and also acknowledge other sponsors we have at the bottom of my slide here.
Thank you very much, Dennis. And so we invite you to come in for the next level of having these papers presented at Berlin, Germany. That is coming up in October. And if you have any other questions, please do give us a shout or send us an email to Dennis or myself. And you can also go on our website to download the white papers, including the biofouling, which has the software code that anybody can actually download for their experiments. The entire tracking wheel construction has been published in IEEE Canada, and we also have our own version of tracking wheel on our website, white paper. So feel free to download that, and also give us a feedback as what you think moving forward should be. Thank you very much.
All right, thank you for that great presentation, Dennis and Raj. Look forward to the days when we can travel normally again, right? Going over to Germany and overseas. So yeah, that should be a great conference, and excited for folks to join us there. We'll open the floor to questions from our audience now. So if anybody has a question for Raj or Dennis, please feel free to type it in your chat function, the questions function on the side of your screen, and I'll ask it to our presenters as they come in. To start things off, Dennis and Raj, maybe I have a couple of questions. Can you explain what is a 2.0 lightweight insulator?
Oh, great. I can take that, Dennis. The 2.0 is basically, as you would see, like we started off this technique, the consulting as for distribution insulators and as well as transmission right here in Canada at Burnaby. And the 1.0 has been developed, and we shared this technology or sold the know-how and technology for about 10 years to Asia Pacific. And so there's one thing that we have seen fast forward is when we started to actually deep dive into this and started to see what should be the next level, just using by say hot dip galvanizing and having to expose that different de-icing salts and algae as well. And then what we see is basically there is the analytics and the data that we have actually moved with our lab conditions is actually helped us to actually move that hot dip galvanizing into more corrosion resistance kind of an element. So a classic example is if you would see a 1.0 which exposed to say magnesium chloride would have a rust that will show up this way. So this is just a quick show and tell, as you can see. And then what we did is we basically modulated the same hot dip and having to run into the same magnesium chloride environment, and you would see actually there is absolutely no rust. And this is really, really important when it actually comes into the areas like station post or a line post where you have those nuts and bolts and threads where you don't actually want to see any corrosion, where it actually consumes time when it comes to line maintenance.
Excellent. Thank you. Thank you for that explanation, Raj. Now you're talking about the Armagolv. Can you explain what is the Cordic Asa Armagolv corrosion treatment? Can you go into that a little bit more?
Absolutely. So basically, Armagolv is a thermal diffusion process. So instead of having to use the zinc in a liquid form, this is used in the vapor form and is baked at a very high temperature to impregnate that zinc into the metal. And thus the corrosion resistance gets to be layered. And I would see, as you would see, like 3,000 hours of salt spray can be easily attained, and it can go up to 10,000 hours depending on the conditions of the environment. So Cordic has pioneered in having to introduce the Armagolv TDG into the utility space, and what Asa has done is basically got into more of an insulator space. A typical example is like a hardware, which is hot dip galvanizing with 3,000 hours of salt spray. I don't know if you can see it. That's a kind of rust you would get, and this is hard to kind of chase any kind of nut or a bolt. So in case of Armagolv, this is how it actually shows up after doing all that kind of salt spray. So this is easy to kind of chase a nut, and we are able to open it up and close any of those features, and we are able to actually do the line maintenance effortlessly. So that's pretty much what about the electrical grade, what Cordic has pioneered in doing. So.
Oh, that's a very stark difference between the two. So. I kind of see that. Now, talking about the same thing, how is the Cordic Asa Armagolv corrosion treatment useful, especially for insulators?
Absolutely. So this is where Asasoft has pioneered it, working with Cordic with their wealth of knowledge that they have attained in having to treat this corrosion resistance, as Cordic has been in the manufacturing since 1898, right from forging of the metal to the finished product. So this is where we started to work with our affiliate partner Cordic. And so, for example, a classic example is, for example, an insulator like this, an insulator which is basically having to have a polymer and the metal parts and the transition. And if this was to be exposed to a power arc, and you would basically see the entire built-in corona ring has been completely destroyed here. And then we would need to make sure that there's no moisture ingress into the inside of this particular fiber rod of the E-glass, right? So so having to do the Armagolv treatment, this allows us to actually even coat the corrosion resistance inside of this particular element, right? So this is what actually makes this particular product extra special. So if you see a product which is actually having a little bit of a darker gray, and you would see the inside of that is also already corrosion resistant. So in case of the way, because the mechanical of the way it gets together is by having to not touch the glass, but just bring it so that it just basically lands on the surface, and we're able to actually introduce the tensile strengths to about 100 kilonewtons. And this is exactly where it makes a whole difference with insulators. And another example is you would see in a station post where you would have the threads like this. So there's no way these threads can be ever coated with any kind of a galvanizing, except what happens with Armagolv. So this is the only way we could actually do treatment of threads. So as a whole, you are getting a product that is basically corrosion resistance, moisture ingress, been defended very well when it comes to polymer and the metal together.
Awesome, thank you for that explanation. That's very cool to see. Again, I'll ask the audience to type in any questions. We have a few minutes, and I'll be happy to ask them to our presenters. In the meantime, Dennis, perhaps do you have anything to add? Any comments that you want to leave our audience with? Any next steps?
Yeah, I think that this is a very cool collaboration and project with me. And to be honest, a lot of the things I've been interested in characterizing on solid liquid interfaces before I had this collaboration with Asasoft really got at some of the same types of questions. But it's, I've frequently said when I've given presentations with a less, kind of industrial relevance or a less immediate applicability, that we really need basic science to understand engineering problems. And now, as a result of working on these insulator projects, I can really see that. I think this is a classic example of how, more bulk level, simpler to implement but cruder tools really don't give you the answers as to what's happening. And it's really necessary to take that deep dive and look at things at the level of molecules to understand these kinds of phenomena. So yeah, I think it's kind of a really cool example of seeing like science in action and being directly applied to an industrially and environmentally relevant problem.
Love it. Yeah, thank you very much. Raj, anything to add or anything that you'd like to leave our audience with?
I would really thank Farhan and the CEA and everyone who came in today for this live conversation series. There's been actually a lot of good feedback, and we continue to pursue this research to the next level and share with the community at large.
Great, excellent. Thank you very much for that presentation and answering those questions. I see there's no more questions coming in, so we'll look to conclude the webinar now. Again, from the CEA, we'd like to thank you, Raj and Dennis, for taking the time to join us. To our audience, thank you for coming. All of CEA's future events and webinars can be found in our monthly newsletter on current affairs, or you can go to the news and events section on our website at electricity.ca. With that, we'll conclude today's webinar, and we'll see you on the next conversation series. Everybody stay safe, and bye for now.
Bye-bye, thank you.